Welcome to the AP Physics Kinematics problem set, so the solutions for numbers 21 and 22. 21, a parachutist with a camera descends in free fall at a speed of 10 meters per second. The parachutist releases the camera at an altitude of 50 meters. Okay, so rereading the question here, descends in free fall. So we know the acceleration is the acceleration due to gravity. The speed of 10 meters per second is the initial velocity. And the camera is released at an altitude of 50 meters, so that's the x value. How long does it take? Is the time for the camera to reach the ground. And what is the velocity of the camera just before it hits the ground? That, of course, would be its final velocity. All right, so let's jump right in here. For A, we're looking for time. We have x, we know the acceleration value, and we have a VO. When we go to our reference table, it seems like with the given variables and us trying to find time, that we would start at x equals VOT plus 1/2 GT squared. G substituted for A. We go ahead and substitute. We have 50 equals 10 times t plus 1/2 9.8 times t squared. Now you'll notice in this problem that the 50 meters is down, the 10 meters per second is down, and acceleration due to gravity is down. Therefore, we do not have to assign a negative value to the acceleration due to gravity because all the information is in a consistent direction, which is down. We could, but if we assign that negative value to the 9.8, we also assign the negative value to the 10 and also to the 50 to stay consistent. Now, as we look at this question, what you should recognize right away here is that we do have a quadratic equation developing, which we would then have to solve. I don't tend to like to do that, so I look at, okay, it would be nice if we knew the final velocity because we could just then use V equals VO plus AT, GT actually. So what I'm going to do is I'm going to pause this problem on A for a moment, and I see over in B that it's asking us for that final velocity. So I'm going to go ahead and calculate that if I can. And we want the final velocity, we know the acceleration, we know the initial velocity, we know the distance. So we could do that in one step with V squared equals VO squared plus 2GX. V squared equals 10 squared plus 2 times 9.8 times 50. Again, all our information is in a consistent direction, so we don't have to worry about sign. Solve for V. Pause the video if you need time to carry through with your algebra and do the calculation. And you should get to 2 digits. V is 33 meters per second. So we have our answer to B, which we can now then come back and use to do our calculation in A. V equals VO plus GT. We're just doing this to avoid using the quadratic. I'm going to use the non-sig fig value of my B answer. Let's see here. That would be 32.9 equals 10 plus 9.8 times t. Again, all our information is consistent, so we don't have to worry about sign. Solve for t. Pause if you need to. And we should get an answer of 2.3 seconds to 2 digits. All right? So sometimes, I guess the moral of the story in this problem is you don't have to do them in the order of A and B. If it's advantageous to do a later problem and get that answer and then come back and use it in an earlier question, then so be it. You don't have to do them in the order given. Okay? All right, let's move on to number 22. A ball is thrown upward from the ground with an initial speed of 25 meters per second. Okay, so we have a ball that's thrown up. And that would be its VO value. At the same instant, another ball is dropped. Okay, so I'm going to switch colors because we have a ball that's thrown up and a ball that's dropped. Whenever you see the word dropped, it indicates to you that the initial velocity is 0. And the building is 15 meters high. Okay, that initially looks like an X value here. All right. After how long will the balls be the same height? After how long is time? Okay. So we'll label that as T. They want to know when the balls will be the same height. This seems to be a bit of a confusing question. So I'm going to start with a well-labeled diagram to try and help ourselves out here. There's our building, or whatever it is. Yeah, building, 15 meters high. And staying consistent with my color designation here, we have a ball that is thrown upward, and it has initial velocity of 25 meters per second. We also have and we're going to call that ball 1. I'll put a little 1 in there. Okay. We also have a second ball, which I'll let be red, that is dropped. Therefore, its initial velocity is 0 meters per second. And we know that they're going to end up meeting somewhere in between. So we'll draw this dashed line, which will represent where they meet. We don't know if it's going to be in the middle. We don't know if it's closer to the drop ball, it's closer to the thrown ball. It doesn't matter. And what we're going to do is we're going to label the distance that the red one falls X. And we're going to label the distance that the blue ball rises H for height. Okay? All right, what do we also know? We also know that both balls will accelerate due to gravity at negative 9.8 meters per second squared. In this problem, it is important to assign G a negative value because we have conflicting directions going on in this question. We have some information that's up, we have some information that's down. So our 25 meters per second will be positive, therefore the down direction, any information down needs to be assigned a negative value. That's a really important point coming up in this question. All right, what else can we establish? We also know that the 15 meters is the sum of how far the ball 2 is dropped plus the height in which the first ball rises. Okay, so we have that in our pocket as well if we need to. All right, let's start with ball 1. What would be ball 1's motion equation? Well, based on all the given information, it would be x equals VOT plus 1/2 GT squared. The x value that we're assigning is h. Initial velocity is 25t plus 1/2 negative 9.8 t squared. Let's clean it up. H is 25t minus 4.9 t squared. What do we have? An equation with 2 unknowns. What do we need? Another equation with the same 2 unknowns. So we go to ball 2. Let's see if we can get a motion equation for that. We start off the same, x equals VOT plus 1/2 GT squared. And here's a really key important moment here. The x value, we can go down here and express in terms of the fact that it's 15 minus h, And we can use that as a substitution here to get h in that equation. However, what direction is that 15 minus h? What direction is that x value, the direction, the distance that ball 2 drops? That direction is down. And because that's inconsistent with h itself, we need to assign it an overall negative value. So subbed in here, x would be negative 15 minus h equals, our initial velocity is 0, so the VOT term is 0, plus 1/2 negative 9.8 t squared. Continuing to clean it up, negative 15 plus h, we're distributing to the negative 1, equals negative 4.9 t squared. Isolating it for h would be, add 15 to both sides, minus 4.9 t squared. The advantage of doing this, obviously, is now we have two equations with the same two unknowns. And so now we can go forward. Let's refocus here. What are we looking for? After how long will the balls be the same height? So we're not looking for the height, we're looking for the time in which they meet at the same height. So our two equations are set up well because they're both solved for h, which means we can now set them equal to each other. So our 25t minus 4.9 t squared equals our 15 minus 4.9 t squared. By doing this, we've eliminated h as a variable, and we can simply solve it for the time, which is what we're looking for. This worked out nice for us in this particular problem because the 4.9 t squareds cancel. So 25t equals 15. So t would be to 2 digits because all our measurements are to 2 digits, 0.60 seconds. Okay? So a neat little problem, similar to other ones that we've done where we set up two equations with two unknowns because of the two unknowns and then solve them simultaneously. All right? We'll be doing numbers 23 and 24 together tomorrow in class.